They're still useful. Bless you. Okay. So again, we'll just kind of reintroduce these because I believe these should be familiar from Algebra 2. All right. So we have something in exponential form here. Here's an equation in exponential form. Okay. Y equals a to the x. So a is going to be some number. Okay. And then x will be your variable, and then y is also a variable here, right? And a, I guess a, we should say a probably has the same stipulations here as our exponential functions. So in other words, we want a to be, well, let's see here. Will that still be okay? I'm going to hold off on that. Yeah, we want a to be greater than 0 and not 1, I think. I think we still want that to be the case here, because then it wouldn't be exponential if it was 1, and then 0 or negative would be kind of funky. Okay. So in exponential form, this is saying a certain relationship is true. Y is the same as a to the x, right? In equivalent, an equivalent way to write that is using a logarithm. Okay, so log base a of y equals x. Okay, and this is an equivalent form. Okay, but written as a logarithm. So this is what you might say logarithmic form. And you would read this as log base a of y equals x, right? That's how we read that. Log base a of y equals x. So the y you can kind of think of as being inside the logarithm there. You can maybe put parentheses around it there if you like. Okay. So it's not log of a times y, it's log of a of y, okay? The y is inside the logarithm there. Okay? Yeah. Good. Just like when you say sine of x, right? The x is inside the sine function, if you remember from geometry, something like that. Okay. Yeah. Yep, right back there in the corner on the bookshelf. All right, so we're going to evaluate some logarithms here, and or you could say simplify, right? Same kind of idea. All right. So for example, log base 2 of 8. One moment. Hello? Sure can. Bye. Maddie G, they want you in the AP office again. Ooh. No, I'm just kidding.
That's 3, right?
All right. Well, we can start doing sets, or if you want to stay after school today, I have until 3:30, so you can do it then. Or if you have fifth block, you can get out of fifth block. I have fifth block planning, so if you want to come in during fifth block, you go too. Yeah. Okay. So you let me know. You think about it. Let me know what you want to do. Yes, Jeff.
Log base 2 of 8 is 3, right?
Yes, log base 2 of 8 is 3. Exactly right. Okay. So if that is not something you're comfortable with, right? If you Jeff just said that, you're like, how did he get that, right? So one way you can kind of make this maybe a little bit easier for yourself is to say, okay, let's just assume we don't know what it means. So I'm just going to say let's let it equal x, some unknown quantity. Okay. You can rewrite this logarithm now in exponential form, right? So just use what we did right here. We have log base a of y equals x. That means we can rewrite it as y equals a to the x. So the y here, what's inside the logarithm, in other words, the 8, okay, you get raised to the x over here. So 8 to the x equals, wait a minute, I did this backwards, sorry. The base here, sorry, the a, k gets raised to the x power there. So it's 2 to the x equals 8. There we go. Okay. All right. And so Jeff was right? 2 to the third power gives us 8. So x is 3.
I get something in this class.
Yes. Good. Okay. And long story short, right, when you see log base 2 of 8, okay, that is asking, okay, so when you see that, that's asking 2 to what power is 8? Okay, that's the question you want to ask yourself. So when you see a logarithm out in the wild, right? Okay, you want to do the base to what power is what's inside there. Okay, and that's the answer to a logarithm. Okay, the answer to, in this case, 2 to what power is 8.
I always think of the small number as being very large, and like what it's of on the other side of the equal sign. You know, the base or the small number to what power equals a large number.
Yep, and that's
Which is kind of the reverse of how it is in exponential, where the large number to
the small number. No, you're right. It does kind of reverse, which makes sense in an inverse sense. So they kind of reverse things
so
like
I just
that.
think of the sizes as reversed.
Yeah. Road question.
I remember something about LN.
Yes, we'll get to that in just a little bit.
Natural logs are confusing.
We'll get to that. Yep. All right. So let's try a few more here. So log base 3 of 81. Log base 3 of 81, or in other words, 3 to what power is 81? 3 to what power is it? We did do it. We did it in the warm-up, I think. Yeah. So what is it? 3 to what power is 81?
4.
Ooh, 4. Yep. Yeah. Again, log base 3 of 81 is x. So 3 to the x equals 81. So yes, x is 4. Okay. All right. Do a few more here, and then I'll have you guys try some on your own. All right. How about log base 3 of 1?
0.
3 to what power gives us 1? 0. Yeah. Okay. Can do.
Must be embarrassing for some people to have the dumbest person in the class understand something better than they do.
Oh, well. Jeff, I wouldn't call yourself the dumbest person in the class. All right.
I mean, I have almost certainly have the lowest grade in the class. I doubt it.
Does that necessarily mean you're the dumbest, though?
Yes.
Grades determine that?
It
The
means
school system is broken.
it means
Right.
it means I understand the material being taught in this class the least. I wouldn't say I'm dumb. I just don't understand this stuff very well.
Okay, so there you go. That's maybe a more accurate representation of who you are and what you understand.
Okay, so now, so the answer is 0.
The answer, right? Yeah, we started with the question exactly, and then maybe I'll just like box it in.
That's why I'm confused.
Yeah, these are kind of weird, right? It's not an equation that we've got. It's like me putting up, it's almost like an expression, really, a logarithm expression, right? If I put up 2 plus 2, you're like, oh, this equals 4, so we just like throw an equal sign. But it's like, wait, which one's where's the work, what's the answer? Well, this is the answer, in the case of like addition, right? So it's the same kind of thing with logarithm. You write a logarithm up, you can equivalently then just rewrite it as, a value. So, for example, here, log base 4 of 2. In other words, 4 to what power gives us 2?
Oh,
4 to the negative 2? 4 to the negative 2 would be 1 over 16. 4 to the 1/2 power. Exactly right, Rohan. Yes, 1/2. This is the square root. Okay, this is the square root 1. Okay. 4 to the 1/2 would give us 2. Okay. All right. Number 4. Let's do one more here together, and then I'll give you guys some on your own. How about log base 10 of 1/100th? Log base 10 of 1/100th. Log base 10, or 10 to what power gives us 1/100th? -2. Exactly right. Yep, that's right. Okay. Very good. So yeah, -2 would be the answer in this case. Okay. And again, sometimes it's helpful to maybe rewrite, what you got here, so you can remember. Think about that log base 10. The 1/100th, you can think of that as 10 to the -2, right? And so then you're really asking a simple question, right? 10 to what power gives us 10 to the -2? Well, it's the -2, right? Right there. Okay. All right, let me give you guys 3 to try here. So y'all try these. All right, so log base 2 of 16. And then log base 100 of 10. And then log base x of x to the 5th. Okay. So do those real quick if you don't mind. Give them a try. 30 more seconds here. Okay, Ethan, what'd you come up with for log base 2 of 16?
4.
4. Right, because 2 to the 4 is 16. Good job. All right, how about Jenna, you? Log base 100 of 10? 1/2, because 100 to the 1/2 power is 10. Very good. And then last one, Tommy, what do you say here? 5, yeah, okay, 5, exactly right. So yeah, we can have exponents show up. Sorry, we can have variables show up there. Okay, the one we probably should state here that x cannot equal 0. Okay, x. Wait a minute. Sorry, is it 0? Let me see here. Because actually, I think 0 would be okay there. 0 is 0 to the 5th. Oh, I just think we normally don't ever have a base 0. That's the other thing. So I think that's why. We don't really have a base of 0. Okay, so, all right, cool. Bless you. So now I want to just talk about a few logs that are special because they are named, okay? So for example, log base 10 of something, okay? Log base 10 is typically known as the common log.
It's used in scientific notation, isn't it?
I think, yeah, this is the one that was used a lot, I feel like, for like accounting in large numbers and stuff like that.
Yeah.
Okay. And things.
Scientific notation is a way to write large numbers.
Yeah.
That's it's a log base, or it's log base 10 of something times like a decimal. That's
Yeah. Yes, exactly. Now,
that's very long.
when you see log base 10, you can equivalently write just log, okay, of that same something. So in other words, if you don't see a base, if it's just log of something, we're going to assume that's log base 10, okay? And that's how I learned it when I was in high school, and that's how our book uses it. But then when I went to college at the University of Maryland, I had professors that would use this to mean the next logarithm we're going to talk about, which is natural log, okay? So they would use, so just be careful, okay? I just proceed carefully, all right? When you're in a math class, and I will say this too, when you go to college, if you take math classes, your math professors are not always the best teachers. They may know the material very well. They might be brilliant people, but communicating it to people that don't know it very well is a challenge for them. So, yeah, Jen?
Isn't the log 10 one LN?
No. ln is log base e. We're going to get to that one in just a second here.
Also, my brother went to University of Maryland,
Yeah.
and he had to drop his major of mathematics because
Yeah.
of the professors.
Yeah. It's just a very, and again, maybe I only have my experience at University of Maryland to really judge this, but I don't think that's the case. I've heard other people talk similarly about this, but basically it's like the professors, they're very brilliant people, but they're sometimes communicating it to a student is difficult for them. Okay, because sometimes you can be so smart you just get it, but then communicate to someone else, it's harder to do. So anyway, just keep that in mind when you go to college. That's this could be talking about natural logarithm. We'll talk about that in a second. Okay, so for our class though, when you see log of 100, okay, we understand that to be log base 10 of 100, which is really then just equal to 2. Okay. The log button on your calculator, so there is a log button on your calculator here. If you go here next to number 7, you can see it's log, right? If you press log, all right, you'll see we have log come up. So this is going to be log base what? 10 on the calculator, okay? So again, the calculator even supports us here. I don't know where my professor was getting that stuff from. But if I type in 100, there we go. We get the 2, right? If I type in, log of 1,000, right, we get the 3, right? So you get the idea there, right? Okay, it works. All right. Another named logarithm is the natural logarithm, or natural log, I'll say, okay? And it is a logarithm with base of the number e. Okay?
The number E.
The number e, just like the number pi.
The color 9.
Exactly. We use e to represent the number. Okay, and it's approximately that. Okay. Yes. Well, remember, in math, we use letters to represent numeric quantities all the time, right? X, y, those are representing numbers. But I agree, it is kind of a silly thing to say. But logarithm of the base of e, okay? E has an origin and has, like, it's kind of this, one of those numbers that shows up naturally, just like pi was a number that shows up naturally. E and pi are kind of similar. They're both irrational, so that means they're like decimals that go on forever and don't repeat. But they don't come up, I would say, like, well, they can, I guess, but like, they're different from like the square root of 2. Right? When you see the square root of 2, you recognize the square root of 2 as like a number, and you recognize it as being this quantity whose decimal goes on forever and doesn't repeat in any sort of regular fashion. When you see pi or e, you kind of your brain has to like give a little pause because you're like, wait a minute, pi is a letter, e is a letter, but we have to recognize these things are actually representing numbers. So just I can throw students off and stuff like that. Okay. If I asked you, and this happens in calculus all the time, if I say, well, not all the time, but it happens in calculus. So for example, if I asked you to give me the derivative of the number 2, right? Well, if you think about the graph of 2 is just a horizontal line, right? 2 is a horizontal line, so what's the slope of a horizontal line? 0, right? So the slope of 2 is 0, right? So the derivative of 2 is 0. And the derivative of any number is 0. But if I say, what's the derivative of pi, you suddenly think, oh my gosh, that's a crazy, I don't even know what that would mean. Pi is like a letter, but it's really just a number. The derivative of pi, 0, because pi would be 3.14. It'd be a horizontal line going through 3.141592.6, et cetera, et cetera. Its slope would be 0. Same thing with e. The derivative of e, it's a constant. The derivative of a constant is always going to be 0. Okay? But throw students off because they see the e and they're like, oh, that's way more complex. So anyway, you will never really see this, although that's not, it's not wrong to write. You just don't really write log base e of x. Instead, you will write it as natural log x. Okay? And you use the cursive L and N there. But if you just write it as script ln, that's fine too. Okay. And of course, we say natural log, but the order is logarithm natural, and that's because I think it's from the French logarithm naturel. Okay, I'm not going to try a French accent or anything like that because that's just kind of, anyway. All right, 3 basic properties of logarithms that arise. And we'll talk about some other properties later. Okay, 3 basic ones though. Log base a of 1. So no matter what a is, if you're doing log base a of 1, what will your answer always be? A to what power gives you 1? 0. It's got to be 0 here. Okay. So if you're taking the logarithm of 1, you're going to get 0, right? And if I type this in my calculator, log of 1, 0. Okay. We also have natural log, by the way. Natural log button. Natural log of 1, also 0. Okay. Second basic property here, log base a of a. A to what power gives us a?
1.
1. Yep, 1. All right, one more basic property here. Log base a of a to the x. A to what power gives us a to the x? X power, right? Exactly right. Okay. Pretty straightforward stuff there, right? It's just, it's maybe not even worth, mentioning and stuff like that. Okay. So, I do want to go through a few things. Let me talk about 3 other kind of problems here. Well, I want to go back. Let me see. I want to investigate a little bit more with logarithm and natural log. Just like 3 little examples I want to go through here. Just kind of help things out maybe. And then we'll graph a logarithm and then we're done. Okay, so it shouldn't be too much longer here. We're almost through. But I just want to go through a few things here. So, for example, and I think we already mentioned this, but I'll go ahead and mention it again here. If I said log of 1,000, okay, right? This is like not basic properties necessarily, but let's just do some examples here with log or the natural log. If I said log of 1,000, okay, normally we know, right? What would this have to be? Okay, right, because this is really log base what? 10. So 10 to what power gives us 1,000? 3, right? Okay. But then if I asked you something like this, log of 54. Okay. 10 to what power gives us 54?
That'd be something close to.
So we can kind of narrow it down here, right? 54, can you guys narrow it down? Between what two numbers is it going to occur? 1 and 2?
Yeah,
Why 1 and 2?
It's somewhere around 0.5 because
Well, it wouldn't be 0.5 because that's not between 1 and 2.
well,
Maybe you think of 1.5?
yeah, 1.5
Okay. So, but why between 1 and 2 though? Why between 1 and 2?
because it's between 10 and 100.
Aha, right. 54, right, is between 10 and 100. So 10, log of 10
0.5 or 0.6
is 1, and then log of 2 is interesting. He put you on as Heidi.
That's my mom.
That's interesting. All right. So right, it's going to be between 1 and 2. Okay, but for our purposes, right, how can we actually evaluate this? And the answer is calculator. Okay, we're going to use our calculator. So we can just type it in for a problem like this, right? So log of 54, well, there it is. 1.732393766, etc. For a problem like that, if you're expected to evaluate it, yeah, you'll need a calculator. We really can't do this mentally. Okay, so yes.
How do people do it before calculators then?
That is a good question. My guess, I know that there in the past, before calculators, but when we were still teaching this stuff, there were tables in the back of a book, and you would look up the answer in a table and get like a decimal approximation. Same thing with trigonometric stuff too, but then how did someone actually like compute out the table and all that? That I am not sure about. Magic, yes. Maybe, I don't know. I'm sure there's some cleverness involved, but yeah. I can look that up, or you can look that up too. So what this then means, right, if I took 10 and raised it to that 1.732, power, we should end up with what? 54, right? And that is the case, right? So if I go back to my calculator here, and I take 10 to the, and I'll just use the answer, okay, rather than having to retype it, I'll just use the answer. By the way, the answer command, if you didn't know that, it's right here above the negative sign, second negative, and it lets you use your previous answer and stuff. So that's kind of nice, yeah.
You can also just click enter when you highlight the answer.
Some calculators don't have that capability, but you're right. You can do that if your calculator lets you like arrow back to stuff, yes. And so there it is, 54.
But it
Goes right back.
did it too.
So,
Mine had the 2. Like, it's 54 point, insert
Interesting.
7 zeros and then 2.
interesting. And that might be just like a rounding error on the calculator's part or something like that too. So.
My calculator also has problems with like substituting anything other than a 10 in the base.
Oh, okay, gotcha. Right. Oh, and so I will say on some people's calculators, let's see, if you press math,
And then you go down.
yeah, log base. If you have the log base command, and I have the pretty type, some calculators you can do any base logarithm you want of anything. So you could like literally just go through the, any of these problems and just type it in yourself. Okay. I have the pretty type. Okay. Some of you might not have the pretty type. Let me just show you that real quick too. Turn off math print. Math, and then go down to log base again. If you've got it this way, okay, then I think it's like the base and then of what? No, I think I did it backwards. Okay, so if you want to do like log of 1,000, you're going to want to type in the 1,000 first, then the base of the logarithm, and there you go. So it's like log of 1,000 base 10 gives you 3. Okay, yeah, that's kind of a weird formatting. I wish they would put the 10 first, but did you put commas in between the two numbers? to have commas. Okay, anywho. That's if you want to use your calculator. And so then, of course, we could do something similar to this as well. I mean, for example, what about the natural log of 2? Right? Is that one that we can compute easily? Okay, and if not, why not? What's the problem with 2? In order to be able to compute a natural logarithm, we need powers of what? E. We need powers of E. 2 is not an easy power of E, right? It's like just some number. So again, we can type into our calculator, though, using natural log of 2, and hit enter, and you get about 0.693. Okay. Okay, and again, if you then took if you took E, right, the base there, E to that power of 0.693 ... Okay, so E to the answer there, you would get back to your 2. There it is. Okay, so. All right. That's that. Enough of that. Let's go then to the last thing I want to do here, which is just graphing a logarithm. See what it looks like. Okay, so we're going to graph log base 2 of x. Okay. Equals y, we'll say. Okay, so again, let's pick some values here to put into our table. Okay, so there's kind of two ways to go about doing this. Okay, there's kind of two ways to go about doing this. One, it would be this straightforward way. Okay, the x values we want to pick. Do we want to just pick any x value here? We want to pick powers of 2. Exactly right. Okay, so let's see here. Oh, and by the way, would a negative x value be a wise choice here? Because think about that. If we were trying to do like log base 2 of -8, we'll say, okay, you're taking a positive 2, trying to raise it to a power and get a -8 as an answer. Is that even possible? No, right? And so we don't want to use negatives here for our domain. Okay. In fact, our domain here will be, greater than 0. Okay. So you want to pick x values that are powers of 2. So for example, 1 would be okay, 2 would be okay, 4, 8, so on and so forth. What else would be okay? What about like 1/2? An x value of 1/2 would also be okay, right? Or an x value of 1/4. Those are also powers of 2 as well. Okay, so that's one way to do this. The straightforward kind of way is you just pick some x values that are powers of your base, and then you get the matching y values here. So let's do that first, and then I'll explain the kind of like another way to think about it too, which I think your Algebra 2 books last year use this. No, you don't need that many points, but I just did it just because, well, it's helpful to see. So what is log base 2 of 1? 0. Log base 2 of 2? 1. Log base 2 of 4? 2. Log base 2 of 8? 3. Log base 2 of 1/2? -1, because 2 to the -1 is 1/2. And then 2 to what power gives us 1/4? -2. Okay? So, plot this here. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. 1, 2, 3. Okay, and then just plot your points. God bless you. All right, so I already kind of gave away the domain here, but what does it look like our domain is going to be according to the graph? Yeah, greater than 0, right? not including 0. So we'll do 0 to infinity. What does it look like the range is going to be here? At least, what's the lower limit of our range going to be? Negative infinity, yeah. And so then what about the upper limit? Is there going to be an upper limit? Will there be a horizontal asymptote here? No, there isn't. It's going to keep increasing. It's going to increase very slowly. In fact, as the further you go along x, the slower and slower it's going to increase. But it will continue to increase, and it will approach infinity. Okay? And I think it's like one of the slowest functions to approach infinity. Because you can see it's just going to start flattening out more and more and more and more as you go. So I think it's like one of the slowest functions to approach infinity, but it does. It's not limited. Okay? Do we have an x-intercept here? Yes, at what point? 1, 0. Do we have any y-intercepts? There won't be any, right? Because our domain is 0 to infinity, not including the 0. Okay. What other notable characteristics do we have here? Do we have a vertical asymptote? Yeah, where?
0.
Yeah, at 0. Okay. At x equals 0 there. So that's notable, right? Okay. This shouldn't really surprise us that we got a graph that looks like this because
that's the inverse of
it's
an
the
exponential.
inverse of an exponential, right? So imagine if we reflected this over the line y equals x, wouldn't it look something like that? Right? So there it is. So, and notice then, with that idea of an inverse, right, the exponential function, its domain was negative infinity to infinity. Reflecting over the line y equals x, now the range is negative infinity to infinity. The range of the exponential was 0 to infinity. The domain then of the logarithm is 0 to infinity. Okay? The x-intercept is 1, 0 in the logarithm. The y-intercept is 0, 1 in the exponential. Okay? We had a horizontal asymptote here at 0. Right? Now we have a vertical asymptote at 0. Okay? So that inverse idea not only just affects how the graph looks, but also all the the characteristics too kind of like flip, if you want to say. Okay? Questions on any of that? Okay. So I believe I've already posted your assignment to Google Classroom here, so you can get started on that.